Hi everyone, I'm Vibha and I'm really excited to be talking to you all today about how network topology can impact the throughput achieved by credit networks. This is joint work with my collaborators at MIT, CMU, and Ohio State. So credit networks fundamentally are networks that enable transfer of money, goods, or services through established trust lines. These trust lines can look as simple as a pair of friends, Alice and Bob, who know each other and are willing to have up to $5 outstanding at any point in time with each other. Or at a much larger scale, this can look like two banks, two Bank One and Bank Two, that are willing to have up to $5 million or a few $1,000,000 outstanding with each other that they settle at the end of the day based on their past banking relationship. And more recently, these credit networks have taken on a whole new meaning with the emergence of payment channel networks as a scaling solution for blockchains that have slow consensus mechanism. And in this case, a pair of users, say Alice and Shanu, may open a joint account where they set aside money that they use to transact with each other without going through the main blockchain. So in this case, trust is established by the underlying blockchain, but they circumvent it when actually making transactions. So the versatility of these credit networks really comes from the ability to chain a bunch of these bidirectional trust relationships into a network that now allows a pair of users, say Alice and Charlie, to transact with each other when they were not previously transacting. So in this case, Alice has a trust relationship with Bob, and Bob has a relationship with Charlie, and Alice leverages Bob as an intermediary to send money over to Charlie. So how does money actually flow on one of these networks? So I'm going to use the example of payment channel networks, but this really extends more broadly. So let's say Alice, Charlie, and Bob have this credit network between the three of them, and Alice wants to send 3 coins to Bob. So when Alice actually makes this payment, what she does is she sets aside 3 tokens on her payment channel with Charlie, locked with a secret key. And Charlie, seeing that this payment is destined for Bob, sets aside 3 tokens on his channel with Bob, also locked with the same secret key. Bob, seeing this transaction and realizing that the entire path has set aside 3 tokens, releases the secret key, claiming the 3 tokens from Charlie. And Charlie forwards the secret key onwards to Alice, claiming his 3 tokens from her. The secret key is really any kind of confirmation mechanism depending upon the actual credit network and the trust relationship that just ensures that Charlie can't run away with the money without actually making a payment to Bob on Alice's behalf. But notice that at the end of this process, what has effectively happened is Alice has transferred over 3 tokens to Bob via Charlie. But also notice that the configuration of this network has changed in a way that all of the tokens between Alice and Charlie are now located on Charlie's end. And what this means is if Alice wants to make more payments to Bob, she can't do so because her channel with Charlie is imbalanced with all of the tokens on Charlie's end. So as we make transactions in these networks, the configurations change. And the key question that we answer with this work is how does the configuration affect the throughput or the success of these transactions? And as we'll see in some topologies, this impact is very massive, and in certain other topologies, it's not. Okay, so let me work with a concrete example to illustrate how these configurations might impact the throughput. So let's consider this same payment channel network or credit network we've been working with, but now everyone has 6 tokens, 3 on each end. And in this situation, if Alice has demand to Bob and Bob has a demand to Alice, Alice is able to send 3 tokens over to Bob in one time step using Charlie as an intermediary, and Bob does the exact same thing in the opposite direction. Because Alice gets the 3 tokens replenished at the end of the time step, she's now able to send 3 more tokens in the next time step, and so is Bob. And so this chain of payments continues indefinitely between the two of them. Let's consider an alternate configuration where the same 6 tokens between Alice and Charlie and Bob are located on the outsides of the 2 payment channels. And in this situation, what we observe is Alice and Bob can't make any payments to each other. And recollect that I mentioned that if Alice wants to make a payment to Bob, she needs Charlie also to be able to set aside some tokens before Bob actually releases the payment in the opposite direction. And because Charlie has no tokens, Alice is deadlocked on Charlie, and similarly in the opposite direction, Charlie is deadlocked on Bob. Bob is deadlocked on Charlie in a way that ensures that neither party can pay each other. And this is concerning because we have the exact same topology, same amount of total tokens. In one situation, Alice and Bob are able to pay each other, in another, they can't make any payment. So let's formalize this a bit more with our simplified model. So here the credit network is really a graph with edges corresponding to channels between different entities or trust relationships and vertices corresponding to the actual entities themselves. Each channel has a capacity, which is the total number of tokens locked into these channels or set aside. In this case, it's 6 for each of the channels, and you can view this as a vector. Now what we have is the state of the credit network is captured using this balance vector B that tells us how many tokens are located on the left side of both of these channels. And because we have the capacity, this is sufficient to represent the state. So 3 corresponds to Alice having 3 tokens with Charlie and Charlie having 3 tokens with Bob. The alternate state that we've been looking at corresponding to the deadlock is a 6-0 state because Alice has 6 tokens with Charlie and Charlie has none with Bob. In reality, this balanced state space is a huge high-dimensional space, which we capture as boldface B. And what this represents is that the balance on each of these channels can be any real valued number between 0 and 6. With this, we have a demand that tells us who wants to transact with whom. And because we have an underlying topology, what this maps to is a set of paths or flows that tell us exactly how tokens move around in the network. And when I talk about the transaction success rate, what I'm really asking is what is the steady state throughput, phi of B, because it depends upon the starting balance state. And this steady state throughput is roughly, you can think of it as an average throughput across, average long-term throughput across a series of rounds, each denoted by time step t. And in each round, what you're doing is you're allowed to send transactions in any manner that maximizes the throughput, as long as the total tokens sent don't exceed the available tokens on each channel. And I'm going to caveat this by saying that all of this throughput is subject to a demand in topology that tells you exactly what the flow of tokens in the network are. Okay, so with this model, if we go back to our examples, what we notice is we've actually been capturing 2 ends of this throughput spectrum. The first case, where the channels are perfectly balanced, corresponds to the maximum throughput, and it's pretty straightforward to see that the maximum throughput is always achieved when all the channels are perfectly balanced. And in this case, this max throughput or max phi across the balanced states corresponds to 6 because Alice is sending 3 tokens to Bob in one time step and Bob is sending 3 back to her. In contrast, our deadlock state corresponds to the other end of the spectrum, which is min phi across all balanced states, which we call phi min, and this is 0 because no one is sending transactions to anyone. In other words, in this topology, phi min is not equal to phi max, and this topology is said to exhibit throughput sensitivity. And this is clearly bad for someone designing topologies because what we're saying is if we slightly perturb the configuration, you might end up with vastly different throughput numbers for these two topologies. These two states for the same topology. In contrast, one might be interested in designing topologies where the phi min and phi max are close to each other, or in other words, the topology exhibits throughput insensitivity. But at first glance, this seems rather hard to answer because what you're saying is I have this huge high-dimensional balanced state space and I'm curious about where the phi min and phi max are achieved, and I don't know a priori where this might be achieved or what the values might be. But it turns out that this deadlock behavior entirely characterizes the throughput sensitivity of a topology. In particular, we show that if a topology has no deadlocks, or in other words, there's no state where all the tokens on a channel are stuck on one end and no payment can move it, such a topology that doesn't have deadlocks also has throughput insensitivity. To get an intuitive sense of why this might be true, a topology that has no deadlocks is essentially saying if you view the balanced state space as a high-dimensional polytope, and you start at one corner corresponding to all the tokens being on one end, that channel can be moved into the interior regardless of which corner you start at. And if this is true across the entire polytope, then it means I can move a corner into the center where the maximum throughput is achieved, so the throughput is equal across all states. A consequence of this first theorem is our second result, where we show that the minimum throughput phi min is achieved at the state that has the maximum deadlock or the largest deadlock. And once again, the state that has the largest deadlock corresponds to the maximum wasted collateral. So if you can extract some throughput from that worst state, you can extract it across all states in the balanced polytope. So does this help us? What have we done so far? We've taken this gigantic balanced polytope and reduced it to just analyzing it at the corners. But it turns out that the number of corners is still exponential in the number of payment channels, and in fact, deadlock detection is NP hard. So there is no computationally tractable way of saying whether a topology has deadlocks or where that might be. But what can we do? So let's take a step back and look at a given topology that tells us who has channels with whom, and the blue arrows correspond to the paths on this topology that tell us what flows are present. And let's focus on the channel between Alice and Charlie, C1, and ask whether this channel can be deadlocked. And notice that this channel C1 has two flows F1 and F2 that are dedicated or are length 1 flows that only go between Alice and Charlie. The presence of these two flows means that if all the tokens are ever locked on Alice's end of the Alice-Charlie channel, the flow F2 can move it towards Charlie's side regardless of what is happening in the rest of the payment channel network. And similarly, the flow F1 can always move tokens from Charlie's end if they were ever stuck on Charlie's end. The presence of these two flows essentially says the Alice-Charlie channel can never be deadlocked. And what does this mean for flow F3 that goes through the Alice-Charlie channel from Alice to Bob? It essentially says F3 cannot be bottlenecked on C1, so you can remove C1 from the perspective of F3 and now analyze this on a reduced topology with only those flows that go through the channels remaining. It turns out that this whole process can be visualized as a peeling algorithm on a bipartite graph where flows correspond to the left side and channels correspond to the right side, and there's an edge between them if a flow uses a particular channel. So C1 in our context has flows F1 and F2 of degree 1, and the red and the blue correspond to the fact that F1 and F2 use it in two opposite directions. Such a channel can be colored both blue and red, denoting the fact that it can be moved in both directions, and you can peel it from other flows such as F3 that use it, and this procedure continues. This is very similar to a to a decoding algorithm for erasure codes, and the literature there tells us that the termination depends upon the degree distribution of the flow nodes, which in this case is the path length distribution. So it may terminate and tell you that the topology is deadlock free, or it may not terminate but gives you a lower bound on the number of deadlock free channels. So clearly this is an approximate algorithm, but how well does it work in practice? To evaluate this, we look at 4 topologies with about 100 nodes each, and on the x-axis we vary the number of randomly sampled demand pairs corresponding to flows, and we assign the shortest path. And on the y-axis, I'm going to look at the number of channels deadlocked as reported by an ILP. And if you look at this, what you notice is 4 lines corresponding to the truly reported number of deadlocked channels. But I'm going to overlay on top of this what is reported by our peeling algorithm. And so if you notice, all the points corresponding to the number of unpeeled channels, which are the deadlocked channels or those channels that the peeling algorithm is not able to make a decision on, matches exactly with the underlying lines corresponding to the true number of deadlocked channels. So in practice, our peeling algorithm is not just approximate and providing a bound, but providing a pretty good bound. So now that we have this accurate algorithm, we can clearly go ahead, find the number of deadlock channels in a topology and compute Feynman. But can we go further? In other words, can we synthesize robust topologies that are deadlock free? And the key insight here is that the path length distribution determines the termination. So can we design good path length distributions and generate graphs that match it? And the rationale behind asking this question is really that we believe that we can leverage existing peer recommendation services such as Autopilot to actually influence Autopilot in the Lightning Network context, to actually influence who connects with whom and in turn impact the topology. So how well does our synthesized topology perform? So to look at this, we compare the max and min throughput normalized to 100% as we vary the number of randomly sampled demand pairs on the x-axis. We first look at a random regular graph, which, as expected, its throughput improves as you increase the number of flows, but the min throughput is close to 0 for up to 3,250 flows. This is because of a large deadlock that involves all channels in the topology. In contrast, the scale-free graph has lower max throughput at a high number of flows, but its min throughput is better than the random regular graph, with it exceeding 0 at 2,200 flows. Our synthesized topology, and all of these topologies have about 300 nodes and 1,500 edges, and our synthesized topology with an optimized path length distribution strikes a pretty good trade-off between these two properties, achieving high throughput at a large number of flows, but also having better deadlock behavior than the random regular graph. So this shows some promise in how these synthesis techniques can generate actually robust topologies that have better deadlock properties. That brings me to the end of my talk, and I'm happy to take questions now or via email. Thank you.